Hi, good morning, everybody. Thank you for joining today's webinar, 3D Digital Image Correlation. It's a next-generation non-contact measurement system. We're coming to you today live from Philadelphia, Pennsylvania. My name is Jack Irwin. I'm a Technical Account Manager at Trilion Quality Systems. I'm joined today by my colleague, Kyle Gilroy from Vision Research.
Hey, guys.
And we're excited to get into the technology, so let's get right into it. So we at Trilion Quality Systems, we're a 20-person team based just outside of Philadelphia in a town called King of Prussia. We've been around for over 20 years as far as it all goes, supporting the ARAMIS 3D DIC software and systems all throughout the US and Canada. We do that not only through system sales, but also through engineering services and continued customer support and training. So Trilion is actually the exclusive North American distributor for a German group called GOM, based out of Braunschweig, Germany. So GOM develops the software, the systems, and everything along those lines for industrial applications, everything that has to do with measuring 3D coordinates and 3D testing. So the product that I'm here today to talk about is the ARAMIS non-contact measurement system. It's essentially an optical strain gauge for full field strain and displacement measurements. We also have the ARGUS system, which is an optical forming analysis system used very often in the stamping and tool and die industry for quality control. Tri-Top is true photogrammetry. It's an optical coordinate measuring machine that allows you to collect static coordinates usually on very large structures, ranging from civil to aerospace applications, and understand static displacements over time. The GOM CT is GOM's newest and most exciting product. It is a metrology CT. It's made for metrology applications, and therefore it's the most accurate CT machine in the industry. And finally, there's the ATOS full field 3D scanner. And that does exactly what it sounds like. It performs full field 3D scans for rapid prototyping or reverse engineering applications. Now what's important is all of these systems work together, and they're also available as services, as to where we come out and perform a one-off measurement for you. Today, as I've mentioned, we're here to talk about the ARAMIS system for non-contact 3D deformation analysis. To give you a bit of background as to the type of solutions that we work with or have been used in the past. On the standard testing solution side, to measure displacements, you might have used LVDTs or laser trackers, extensometers, string pots. For vibrations, you'd use accelerometers or laser vibrometers. And finally, for strains, you'd use strain gauges, strain gauge rosettes, extensometers, what have you. Now, these are all great techniques if they're used effectively, but the problem is that most of them are contact methods and they're single points of analysis. What's more is they're pretty tedious to work with. If you misplace them or if they come off during a test, you'll need to place them in the correct spot in a new test, so you will have to retest. Now these tools, they are used to validate finite element models, FEA in the industry, and FEA is a great technique, but it is an analysis rather than a measurement. Your outputs are really only as good as your inputs. So what the ARAMIS system is, it's really a great marriage of the two because you're collecting full field non-contact measurements. Those measurements are extremely similar to finite element models, as you're seeing here, between our measurement in the center and the finite element models on the right side. And for that reason, it's used to more intuitively and effectively validate those models, and it does so at a level greater than or equal to the traditional standard testing solutions. Bit of background as to how the system works. It works very similarly to your eyes. We have a left camera and a right camera, and we're tracking a fiducial marker. Now those markers come in two forms, either a single point, with which we can perform point tracking, or we'll apply a speckle pattern, generally with spray paint or something else that can create a black and white contrast, such as what you're seeing below. And with this, we can collect full field results using a technique called digital image correlation. So you see the types of applications that we're involved with. We do everything from tensile tests to shear tests to complex geometries. So we've used Vision Research's great cameras and some drop tests that take place at the NASA Langley Research Center, where they're doing these drop tests at the Space Flight Center. But our motto at Trilion is if we're able to see it, we can measure it. So anything that, any material or any structure we want to check out and see, we're able to do so. Now to summarize here, why ARAMIS is such a great technique and why it's the ultimate multi-purpose dynamic sensor It's a non-contact method of measurement, and it collects full field results. The types of results are generally displacements or strain maps, but we're not limited to that. We can do accelerations, velocities, shape change, trajectories, what have you. We do that from the very small scale, think millimeter size, to the very large, the several meters in size. It doesn't matter what it is, as long as we're able to see it, we can measure it. Those results, as you've seen, they're very similar to finite element meshes, so our results go on to validate those models effectively. And we do that from the very slow speeds, static test to quasi-static test to extremely fast tests, where we're getting into the hundreds of thousands or even millions of frames per second. And with those types of outputs, we can perform integrated vibration analysis. But most of those applications can only be done with our friends over at Vision Research and some of their great cameras. I'm going to pass off the microphone here to my colleague Kyle Gilroy, who will get into a little bit of detail about how those cameras work.
Oh yeah, thanks Jack. So yeah, before I get into the technical details and all that fun, I'm going to introduce Vision Research. We are a relatively small company located in the town of Wayne, New Jersey. We're about 40 minutes west of New York City, right there in that purple star. The company actually started as a family-owned company in 1950. They were the Jansen family, and initially they focused on photographic analysis. They later transformed into Vision Research in 1992, where they focused on building, designing state-of-the-art high-speed digital cameras, otherwise known as phantom cameras. In 2008, we were acquired by AMETEK, and today we're comprised of roughly 130 employees worldwide. And today we still continue to design and engineer high-speed cameras to meet the needs of researchers, engineers, developers worldwide.
All right, guys. So here we have two 2640 phantom cameras in a stereo configuration. We have them on a bar at a fixed distance and at a fixed angle. We also have the ability to adjust the height and also roll around the room if we wanted to. And in particular, here we have a 100 millimeter Zeiss lens, and we have on the back of the camera here, in order to have synchronization, what we have is we have this camera acting as the master camera, where the f-sync signal from this camera will be fed into the f-sync port of this camera, and I'll go over the software about how we can configure that. And we also have here a hardware trigger, a BNC hardware trigger going from the master camera to the slave camera, and here we have a pickle switch. It's very important not to use Ethernet to do your triggering, because Ethernet is a serial way of triggering things. So basically you have a parallel way of triggering the cameras using the pickle switch. So now I'm going to invite Jack to come in here to help me calibrate the cameras. I'm going to turn on this light here, this GS5 light. And now I'm going to be over at the software here now. And basically what I'm going to do is I have my two cameras. I'm going to close them and reopen them so you understand what I'm talking about. So I'm going to go into my live tab, open up camera 0 and camera 1. And currently the cameras are operating off their own f-sync. So I want the slave camera to operate off the f-sync of the master camera. So what I'll do is I'll make sure I double check what is left and right. So camera 0 here is my left camera, and my slave camera is here on the right, so they're both active. So I'm going to click camera 1, and I'm going to go into my advanced settings drop-down menu. So I want to click advanced settings. I'm going to go to from sync imaging to internal to external, and I'm going to note the serial number down of the master camera. And this serial number can be found just by looking on your camera. It's right here. It's 21111. I'm going to enter that. In the upper part of the software, you'll see now that it says f-sync. So what that means is now that camera is running off the F-sync of the master camera. All right. So now if I go into my Cine settings, I can look at all the different camera settings. So now I have the master camera configured at 2048 by 1952 at 6600 frames per second, and my exposure time is 60 microseconds. Now if I wanted to make a change here, any change let's say I want to make a change to the resolution. If I want that to reflect into the slave camera, I want to lock these cameras together. Okay, so this red border means that they are locked. All right. So now I'm ready to take my calibration images. So what I want to do is now click this arrow, and we have this new snapshot. It's called the Sync Snapshot menu. And inside this little menu here, I can see that I have my master camera with the correct serial number and also its name. And I also have another camera here, the slave camera, with its respective serial number and also its camera name. And to define the file name, I'll click this file name button. And because we're doing a calibration, let me delete this old file here. The first thing I want to do is define my test name. So in this case, I'm going to go into Setup and call it Calibration. It's already typed there. Close it. So now, if I look at this file string, basically, it'll automatically put the test name, and then this slash means that a folder will be created, and then the name of the camera will be written as another folder, and the name of the TIFF will be the name of the camera, and the dash mark will the dash sync snap 6 represents the name of the TIFF, the number of the TIFF, with a padding of 6. So for example, you'll have 6 digits. Now, if you wanted to customize your naming convention, you can go into Insert File Name, and you can actually configure it how you wish. So we have snapshot number. If you wanted to put 1 digit, 2 digits, 3 digits, so on, after the file name, you can do it here. You can stick the camera's serial number into the file name if you wish. You can also include the image time. Again, the camera name as we did. The test name's already in there. And there's also some suggestions that you can choose from. Okay? So now I'm going to go to Save. And I get an error. So I'm going to make sure I go on my desktop and then click Save. Here I have my image formats. It's a TIFF 8, which is what we want. If we want to change that, we can go back into the file naming. This R represents a reset. So since we did 14 calibration images previously, that's what it's set at. I want to press R to reset it. It says, do I want to reset it? I said yes. And I can also explore the file to see if there's anything inside. So right now there's no file on my desktop with that naming, so nothing's there. That's good. Now, to enable the hardware trigger, I'm going to click this snapshot button, and now my cameras are ready to collect sync images. And Jack's just going to tell me when to take some snapshots.
Right. Okay, so we're going to perform a calibration image sequence here, and we're going to go ahead and start where we have our artifact set up. Go ahead and hit that, Kyle, the first image. Essentially what this process allows us to do is to go ahead and snap, is to calibrate for a 3D field of view. Go ahead and snap, Kyle.
Also, pay attention to the fact that right now we're dropping files into a folder that we defined. And we can watch this in real time as we do it, just to make sure we are indeed saving and capturing our files. Snapshot.
So as you see, now we have 4.
Okay. Put this back up. The other thing that this calibration sequence allows us to do is to account for lens distortion. Right. Okay, go ahead and snap there, Kyle.
Okay.
Snap. Other one. Final one on this side. Snap. Okay, go ahead and snap that. So last sequence here, this one, go ahead and snap. Go ahead and snap. And one final one here. And this should allow us to calibrate. Go ahead and snap, Kyle.
Alright, so now I populated this folder called Cam0 with 13 calibration images. If I go back, I'm going to check the other camera. And indeed, it has its own set of 13 images. So now, what we did actually when we named our files is that we named them in such a manner that the software, the GOM software, will automatically read that file name and that folder location directly into their software so that everything is automated. So we try our best to basically make this as easy as possible for the user.
So the way we discuss high-speed cameras in general is we talk about them in terms of throughput. And because of that, that's actually kind of how it dictated how we name our cameras. So whenever you hear the name of a phantom camera, what you should think about is the string and also the numbers that come with it. So the code is basically the family, the throughput, the resolution, and the iteration. So the two examples I have here are the VO990, we also call that the VO4K for short, and also the Phantom V2640, which again, we have these cameras here today. So if you look at the naming convention, the bolded black letters are the family names. So we have the VO series and the V series. And just looking at the V2640, in red there, we have the throughput of the camera. So throughput is basically the number of pixels per second that are coming off the sensor. And then we have the resolution, which is in megapixel. And then we have the iteration of the camera. So if there's a major revision done to the camera, you'll get from 0 to 1, and from 1 to 2, and so on. So for the V2640, it can do 26 gigapixels per second at 4 megapixel resolution. And if you do that little division there, you do 26 divided by 4, you get roughly 6,600 frames per second. And because it's the first camera of its kind, it has a 0 there as its iteration. And there are some pictures of what a VO and a 2640 look like. And more recently, actually, discussions about high-speed cameras have evolved from talking about throughput and resolution and frame rate to now talking about a lot of the features in the camera. And the V2640 is quite special in that we actually designed a series of different modes that can be applied in the camera. And the modes are in this camera: standard mode, high-speed mode, bend mode, high-speed bend mode, and bright field mode. The standard mode, the key difference with standard mode is that it has something called correlated double sampling, which I'll discuss in the next slide. Ultimately, that allows you to have a cleaner image at the sacrifice of a little bit slower frame rates. So in this mode, you can do around 4,800 frames per second at 4 megapixel, and your ISO is around 16,000 in daylight. And the read noise is very low. It's 7.2 electrons. Now in high speed mode, all you're doing is you're toggling off that correlated double sampling. So what that allows you to do is go 6,600 frames per second at 4 megapixel resolution. And as you noticed from the previous mode, you can go a little bit faster at the sacrifice of a little bit more noise. And in this case, the ISO is around 12500 in daylight, and the readout is 18.8 electrons. So as you can see, it's a little bit noisier on the floor. And then we also allow you to bin the sensor. So on the right there, that's a little section of a pixel array. And basically, I drew a red dotted line around a 2x2 pixel family. And that will represent a new pixel in bin mode. So what you're doing is you're ultimately making a sensor that has bigger pixels in a lower resolution. So now at 1 megapixel resolution, you can go up to speeds now with 18,000 frames per second. And because you have a larger pixel, you get sensitivities up to 25,000 in daylight. And your readout is around 12 electrons. Now you can also do high-speed bin mode. And just like previously in high-speed mode, you're just toggling off that correlated double sampling to get that faster speed. So in this case, you can go 25,000 frames per second at 1 megapixel. And again, same ISO because you have that same pixel size. And then in this case, again, you have higher read noise, which is your roughly 30 electrons. And lastly, we have bright field mode. And what bright field mode is, and it's far more unique than the other modes in that we are allowing the user to effectively increase the full well capacity of the pixel. So what that does is it allows you to get a much better signal to noise ratio at the sacrifice of lower sensitivity. So you see the ISO is really low. It's around 2500 in daylight, and it goes 6600 frames per second at your 4 megapixel. So again, this is for people who are looking for really great signal to noise ratio and who have a really bright event because your sensitivity is relatively low. And in this mode, you're going to be able to resolve the details in the bright regions of your image in that dynamic range. And on the far right here, I just show you, if you open up a 2640 camera, basically you have those 5 modes that are selectable, and you can just toggle them off and on quite easily. Okay, so now I'm going to talk about the advantages to having a high resolution sensor for your DIC measurements. Okay, so there's 2 key aspects when you want to achieve great spatial resolution for your measurements, and those are pixel resolution and also your noise floor on your sensor. Okay, so the first thing I want to talk about is the pixel resolution. So we basically try to have enough sensors available with these different pixel densities to fit a wide variety of application needs. All right. So in short, the smaller the pixel, the higher density of speckles you can analyze on your sample. All right. And with an increased density of speckles, it'll correlate to your high resolution. So if you look on the right there, I have a typical CMOS sensor, and this just gives you an idea of what the aerial density looks like for the different sensors. So on the top we have a 1 megapixel sensor, and then underneath that we have a 4 megapixel sensor, and on the very bottom we have what would look like a 4K or a 9 megapixel resolution sample. And today, basically because of how throughput is, typically what you see is that the frame rate will be inversely proportional to your resolution right now. So for example, the 1 megapixel camera can go up to 25,000 frames per second, whereas for example your 9 megapixel will go roughly 1,000 frames per second. All right. So the other key feature is the noise floor control. So as I mentioned before, we have a variety of different modes on, for example, the 2640 that allows you to modulate your noise floor. So if we take a look at your bright field mode, I talked about how you can modulate your full well capacity. So what you're doing is you're going to be, again, trading your signal to noise ratio for a lower sensitivity. So if you really need finer, lower noise in your bright regions, you may want to use this mode. And then the other thing to consider is the correlated double sampling. So if you go in standard mode on the 2640 versus the high speed mode, you're basically turning off that CDS. And what CDS is for every frame that you capture, the sensor is actually sampling the pixel twice, and it actually allows you to lower your read noise. So it'll take your read noise from 18.8 down all the way down to 7.2. So you can get a really clear image, a really clean image in a really low noise floor by toggling on the CDS. And the obvious disadvantage is you're just lowering your frame rate, right? But some people may need that noise at the sacrifice of that frame rate. All right. So just to give you another look at this, if we go ahead and speckle these aerial views, you can immediately see the advantages, right? So for a 1 megapixel image, you may be only able to see 1 pixel per that area on the sensor, whereas in a 4 megapixel, you may be able to resolve 4 speckles in that same area. And even a 4K sensor, you can go ahead and resolve 9 different speckles in that same area of the view of your sample, which gives you a lot of advantage if you're looking at some really high spatial resolution imaging.
And that's important to us too, Kyle. On the DIC side, we definitely traditionally work with higher speed and higher resolution cameras. It's not so often that we get to pair both of them together like we do with some of Vision Research's cameras here. The tools that you mentioned for bright field mode and correlated double sampling, they're really terrific in conjunction with the ways that we can bin or reduce frame rates in order to record faster working with your cameras. So these are really great points.
Yeah, thank you. All right. So I just want to kind of show you some data that I captured. This is just a general control experiment. It's always good to go ahead and just test these different modes to see what it'll give you. So here we have I took the camera and I basically pointed it at a bright rectangle, and I toggled the modes. So I took an image with standard mode and I took an image with bright field mode. And the only thing I made sure of is that I maintained each image at the same gray value. So I made sure that each of the modes were imaging that white rectangle while it was sitting at 3800 gray value. And just by moving those images into image J and doing a line, basically drawing a line across the image and plotting the gray value versus the distance in pixels, you can immediately see that the bright field mode, because it has this deeper full well, you can immediately get your lower noise floor. In this case, your lower shot noise, your lower normalized shot noise at 3800. And if you look at standard mode, you can see it's a bit noisier at that same gray value. So I want to talk about an interesting feature that's actually designed right into the sensor, and it's a feature called image-based auto trigger, or we call it IBAT. And what it allows you to do is automatically trigger the camera based on motion in your event, right? So if you have an event that has relatively large contrast, that can be used to trigger the camera. And the way it works is, on the left here, I drew 11 different frames. So you can think of these frames as being saved into a RAM buffer. All right, so frame 1, 2, 3, 4. The way IBAT works is basically you're going to define a checkup interval. And the checkup interval is actually how often the camera will save a reference image. All right. So once a reference image is saved, and that's a red frame here, you're going to have subsequent frames after that. So 2, 3, 4. So what happens is with IBAT is that, and this is done on the fly. All right. So image 2 will be compared to 1, image 3 will be compared to 1, and image 4 will be compared to 1. And if the difference is substantial enough, the camera will automatically send a trigger out of the back of the camera. And a reference frame, again, is recaptured every checkup interval. All right, so at image 5 there, you have a reference frame. And then 6 is compared to 5, 7 compared to 5, 8 is compared to 5, and then the process repeats itself. All right. So as you can imagine, if you have a small section of your pixel array on the right, and let's say you're looking at a little BB being fired across your, your field of view, and the background is completely bright, your BB is going to be dark. So dark values are, you can think of a gray value of around 10. And the background will be a gray value around 4,000. All right, so what the camera is doing is essentially going to compare the gray values of the IBAT region to the reference frame. So it's constantly comparing these reference frames to frames that come after. So again, if we want to see how this feature is working, really what's happening is you have a reference frame, okay, and the reference frame is going to be ultimately subtracted from your subsequent frame. So if you were to do that crude subtraction and look at it, what it equals on the rightmost side here, when you subtract a gray value of 4,000 from a gray value of 10, for example, you're going to have a change in pixel value of around 3,900 gray value. So that's going to be, your, a gray pixel. And then in your background, you're going to be subtracting basically, a white from a white. So you're going to get a 0. So as you can see in this particular instance, this object shifted 1 pixel distance to the right. So any pixels that had a very large change in the pixel value will be registered as a relatively large change in the event. So if you sum up all the pixels that had a large enough change, it may actually obey your IBAT criteria and send a trigger signal, right? So again, all these parameters are user defined. So we allow the user to basically apply this exactly to their application. So they can define basically the checkup interval, the threshold values, and also the percent area that the object has to change in order to register a trigger. So this is something that is fairly unique to the sensor. So this is just a typical workflow. If you ever wanted to do an experiment where you have an object coming through your IBAT region and you want the camera to automatically trigger, but at the same time, you also want to see the trigger signal. So you have a camera and it's connected to your DAC. This is a data acquisition unit. And then all this can be operated within a software interface. And this allows you to ultimately see the video against the IBAT signal. So there we have on the rightmost side, we have an object coming through the IBAT area. And once it satisfies the IBAT criteria, you can see that on the right, the signal will go from a +5 volts to a 0.5 whenever the IBAT criteria is satisfied. And that will trigger the camera to collect frames. Another feature that is of interest to a lot of users doing a continuous event, whether it be rapid gunfire or whether it be a doctor hitting on a medical instrument over time continuously, is something called continuous recording, or some other people in the machine vision world call this buffer balancing. And what it essentially is we allow the user to break up the RAM buffer into partitions, and you can break it up into 2, 20, 64. You can break it up into small pieces. And then you can configure the software to automatically save that partition during your continuous recording event. And the interesting thing is that once you fill up one partition and you're waiting for the next trigger, that partition that is already full can automatically be saved while the next recording has happened. So let's say you have 64 partitions and you want to trigger this camera every 5 seconds, right? So instead of recording to the whole buffer and then after the whole experiment is over downloading it all, you can actually just save it as you're going, which will save you a lot of time in your experiment. All right, and again, this can be done cyclically, where if you get to your last partition and you want to start writing to your first partition, continuously, it can automatically write to your first partition space, so long as it's saved off the partition.
What a great feature.
Yeah.
Unlimited recording.
Yeah, exactly. You can do it continuously, and it saves a lot of people a lot of time. Especially in these applications that have very repetitive applications. Yeah. So because we're working with sensors that have high resolutions and high speeds, it is of critical importance to put a focus on the download speeds. Okay. So now we're working with frames that are in the 4 megapixel and 9 megapixel range, and relatively large RAM buffer sizes. So what we allow the user to do is utilize a 10G Ethernet speeds. So typically, when you're downloading at 1G speeds, to example for my laptop, you're going to see download speeds around 200 to 500 megabits per second. If you were to select a 10G download pipe, what you'll see is that you can increase your download speeds all the way to 3 to 5 gigabits per second. And actually, the download speeds will become a function of what type of memory storage you have on your back end. So if you have a really fancy SSD, you can actually reach all the way up to 7 gigabits per second, which is something we did in our factory. And what we also see is that depending on the storage capacity of your SSD, which will also change your download speed. So the less space you have on your SSD, in general, it'll start to throttle down your download speeds. All right. So if you ever wanted to test this, what you can just do, go right into your control panel, and once you're downloading off your video file to your PC, you can just open up the performance menu, the performance tab in your task manager, and look at what the Ethernet is performing at. So in this case, we're showing that it did at 4.5 gigabits per second through that pipe. So really useful for people who struggle with download speeds and who want to save time, ultimately. So now we're going to take a look at a device drop. Here we have a tablet device, and we have just marked it up. We had a speckle pattern on there. So Jack's going to replace the calibration grid with the tablet, and he's going to mount it up using here this non-marked water bottle. All right, so we're trying to put the tablet roughly in an area where it will impact. So go ahead, you can loosen that and bring the cameras down to about. That's good right there. Did you sign it?
I did. Yep.
All right. So I'm going to rotate it a little bit. Should we just move the tablet as such? All right, if you can move the tablet to get focus. So we have a nice little feature here where you can toggle the digital magnification. Take the hand and drag so you can see the very edge. So you're a little bit out of focus here. So can you rotate it so that it's square? All right, that should be okay. All right, so both images look like they're in good focus here. All right, so now I'm going to configure the software to do a stereo recording. So I'm going to go into my camera settings, and because we want to do multiple drops, I'm going to partition the camera so that it has 3 partitions. And it's going to ask me if I want to erase the cines from the cameras. I do, so I'm going to delete that. So now if we go back and forth between the 2 cameras, we see that they are indeed partitioned. All right. And we're going to do this shot here at 2048 by 1952 at a sample rate of 6600 frames per second, and our exposure time is 60 microseconds. Always make sure we do a CSR before we do our shot, which is just essentially our black reference. And we want to trigger the camera as soon as we hear impact. So I'm gonna pull this trigger position to the very middle of the frame buffer so that we record a little bit before and a little bit after the trigger, the impact, basically. So now I'm going to enter into capture mode. And I'm going to get my pickle switch handy. So whenever Jack is ready, I'm going to trigger upon impact. Okay. All right, let's do it. Perfect. And again, the cameras are set up such that as soon as a recording is fills a partition, it automatically saves to a file of our choosing. All right, so what we have here is we have the results from our last drop. And again, everything is in red here because these cameras are locked together. So that means when I go to my trigger position, when I pressed it, both cameras should move to the same location. So if I drag this pointer to the right location, I'll be able to exactly see the moment of impact for both cameras. So as we see here, now we have a nice focus when it comes down. And what we can do here is we can actually zoom in quite a bit. And we can kind of see the moment of impact. So this might be too close. So this should be just fine. So as it comes down, I can change my play speed here to play each image. So we can watch as it slowly comes down. We can look for the deformation of the corner of that tablet. And slowly but surely, it is going to impact the table. And you can see the propagation front as it impacts. And you can even see some movement between the screen in the very bottom of that tablet. So you have some very interesting oscillations here along that edge too. So this will make for really interesting footage for some analysis.
Yeah, let's take a look at that, Kyle.
But before we do that, I want to show you some other interesting features that we have that you can do for your analysis. So again, if you want to shorten your video, right? Let's say we only want to look at the impact event, right? We don't want all those frames. We don't want to bog down any other software. We can set this little mark in and mark out. So I can drag it to here. Got my mark out. All right. So now if I go ahead and save, I'm just saving this short region of the RAM here. All right. So now if I go to Save Cine, go to my desktop, I already have my TIFF folder ready to go.
We will upload a 3D image series, so we'll have the TIFF stack from the left camera, the TIFF stack from the right camera, as well as the calibration file that you saw during the presentation there. That's already been done. This project's been worked on a little bit in order to get you guys good access to the data here. So I've gone ahead and done a few inspections. We've taken that tablet here, and based on the pattern that we had applied to it, we are able to create this surface component. The surface component is this gray object that you're seeing here. Now, what's interesting about this surface component? Well, first of all, it's over 10,000 points of data. It's a whole lot of information to pull from. But what's more, in this view, we can have a pretty good idea of the mesh structure, meaning the relationship of all these data points all throughout the project, right? So we can see those intersection of the data points, where we're collecting information, and how we can interact with it going forward. So with this, I've actually created this surface component already. I've established a coordinate system for us to work in. I'm actually ready for us to see an inspection, right? So in this case, the deflection of this tablet is pretty interesting, right? So I'm going to take a look and see the overall global displacements here over the course of this test, and go ahead and reprocess that. So here we are. This is our baseline here. I'll put the image series back on so you can track along with us as this is falling. So as that impacts the table, we're getting changes in color, right? And those changes in color represent the change in magnitude of displacement that's happening. So if I roll back here to around this 140 mark, I notice that there's some pretty interesting behavior taking place. So of those 10,000 data points, I can select any point that I want where there might be interesting behavior and get a live readout of the displacement information. Those points are tracked over the course of the test, and as this falls to the table, we can see the resultant displacements.
Wow.
Just until they come out of our field of view and we can no longer track. Isn't that cool?
That's awesome. Yeah.
We can do a couple other inspections here. I did resultant displacements. Might be interesting to check out displacement in the z-axis, for instance. We have our coordinate system defined here again for your information, so that's closer or further away from us, from the cameras that is. So we're going to reprocess that and track those measurements as well. And once this is calculated, we're going to be looking at very similar results as to the last inspection that we had created, but this time it's going to be directional.
So is this relative to the rigid body, or is this complete displacement period?
Really great question there, Kyle. And what it is, it's relative to a rigid body. We're making this rigid to itself, as a matter of fact. As this is impacting the table, all of our measurements are relative to it. Without that, we don't really have context for these displacement measurements. Right. And that's just, I can actually show you what it looks like if we have the rigid body motion compensation disabled.
Yeah, and I think from a customer standpoint, whenever they want to characterize their device, they could potentially learn the threshold of strain that the instrument can take or the device can take before it breaks. So it's kind of neat.
Yeah, it's a very pertinent application. We have several customers throughout the U.S. and Canada doing just that. Here's an example of that out-of-plane movement with the rigid body motion compensation turned off.
Oh, I see. Mm.
Yes, there's something to see there, but it doesn't make as much sense in the context as when that is defined. So we collected a whole lot of great measurements from one project file there. As you see there, we were able to collect acceleration, strain, impact velocity, full 6 degrees of freedom motion tracking, all from the same image series and project file. Right? And what's more is we really collected a whole lot of great data density. Now, this project was over 13,000 points compared to our traditional high-speed project with a lower resolution sensor. We're looking at about 3 to 5 times more data density. Now it's a question of where we go with the data. We can leverage quasi-static systems in this case in order to create 3D point components, or create a point cloud, align our tablet here to a CAD model, what have you. The possibilities are endless. Now it's a question of learning how to do that and learning how to go forward with it. So Kyle, you had some notes about the Phantom Academy?
So introduced in 2018 is a concept we call the Phantom Academy of High-Speed Imaging. And ultimately what we do is basically we have a lot of customers coming up to us and asking us for really advanced application-specific short courses. So some of the courses that we are planning to teach are focused on data fusion and signals, PIV, particle image velocimetry, how to characterize transparent flows, microfluidics, ballistics and range applications. We'll do one on digital image correlation, and also we're always open to looking to develop custom courses.
Thank you, Kyle, and thank all of you for joining us today. It was a great pleasure to introduce both of these technologies to you, both on the ARAMIS digital image correlation side, as well as Vision Research's high-speed cameras and their great capability. Noticed several questions came in over the course of the test, so we'll be answering them in our Q&A session. We'll try our very best to get to all of your questions, but if we don't, we will try to follow up with you via email or telephone in the coming days or answer them in a good way. So thanks again for joining us today, and have a great rest of the week.
So we have a software, it's called GOM CORRELATE. What GOM CORRELATE allows you to do is interact with these 3D projects, similar to the one that we just collected. So this software is available for free online from GOM.com. We'll be able to send you guys all the links, all the attendees today, so you'll have access to it. And you can interact with those projects in a very similar way to what we just did when we did some bare level post-processing. So there's also the professional license, GOM CORRELATE Professional, that you can try out for free over the course of 30 days. It allows you to have access to advanced features such as Python scripting engine. We have a Python scripting engine within our software. You'll be able to access it, work with those scripts, as well as some of the other higher level functions of the software. So it's a really great tool, not only for learning how to use it, but also for continued training and getting acclimated to it in the first place. So I will move on to the second question here. All right, and then we had Sharandeep who had asked, why were dot stickers used in the tablet drop? The answer to that is we are not limited to just full field results with the pattern, as you saw. We are also capable of performing point tracking, right? And so a reason you might want to do that, for instance, is if you're only looking for discrete points over the course of the test. It could be far less data processing that you need to go through in order to complete that. So we have the choice when we're starting a project to either do the full field results or the point tracking. So that's why they were used. They weren't used for this specific test, but we can go back in post-processing and do some inspections with them. All right.
Yeah, I can answer this one.
Okay. I'll let Kyle answer this next question here.
Hey, we have a question from Philip, and he said, what version of PCC has the naming for DIC integrated? Thanks. So basically, this is it was a beta version of our PCC, where we plan to do a limited and general release in the future. In the meantime, I'm more than open to sending you an updated version that has all these features included. So in a follow-up, we'll basically, I'll send you a version that you could use, and then I'll give you some dates of when it will become available. So, yep.
Right. Thank you for that question. Another question from Chandradeep. Can you show the workflow? So just now we had shown kind of a high-level workflow of the displacement measurement that we were looking to do. So that is basically all there was to it as far as it goes for the post-processing. As you're getting acclimated to the software, there's also a series of YouTube tutorials that walk you through the workflow of the software, so you can get used to it and acclimated yourself. And of course, we're here as a support team for you if you have any further questions on the software. Of course, we'll follow up offline with you to go through the specific project if you want to work on that. Okay. All right. So, we're just getting a couple more questions in here. Another one from Ryan McIntyre. Would 3 or 4 cameras make a more accurate result? That is a good question, Ryan, and potentially it could. So similar to what Kyle was mentioning during his side of the presentation, we're looking to have good pixel coverage of whatever object that we're interested in tracking. So if we're tracking a large object with one camera system, potentially those pixels will be spread thin over the course of the structure. So if we had more camera systems set up across the structure, we would have greater pixel density and potentially more precise results. Generally, that only comes into play with larger structures. But yes, we do have that set up. It's called multi-sensor, and you'd be capable of doing it with that.
Oh, we have another question from Juan Pasmino. He said, "Is this feature to capture 2 snapshots for DIC calibration in PCC 3.4? It is not yet included." I have the email of everybody who attended this webinar, so anybody who's interested in the updated software, I'll be in contact with you. So Juan, I will reach out to you.
Okay, another question come in. You talked about binning for the 2640, Kyle. What method do you recommend?
Yeah, so that's a great question. So on the 2640, for example, we have those 2 modes where you can do standard and then binned mode. And it really comes down to your application. So if you have an application that really demands your high spatial resolution, then you're going to want to use your standard mode, and it'll get you more, higher pixel density, and also toggle on your correlated double sampling to lower that noise floor. But if you're starting to struggle for speed, and you can kind of give up a little bit your resolution and your noise floor, then we'd recommend you go into bin mode, because you can dramatically increase your frame rate and therefore your results. So good question.
We had kind of 2 questions that were similar as far as it all went. One was, how do you calculate the uncertainties, and what's the resolution of the DIC measurement? So that is a function of the resolution of the camera and the size of the object, right? So we'll when we're working with a larger object, for instance, we have potentially lower displacement accuracy as far as it all goes compared to an object that's smaller. The same goes for the resolution. If we're working with a higher resolution sensor, we'll have greater pixel density on the object, and from that coverage, we'll have greater displacement accuracy. Strain values are pretty much uniform throughout. It is strain is just the change in length of the original length. So we have a pretty firm bottom of about 50 microstrain as a noise floor for that. Potentially better or worse depending on the application. But those are traditionally the different levels of DIC uncertainty measurements or noise floors or resolutions that you can expect. I think we don't seem to have any more questions in the queue. We're also running a little bit low on time. Oh, we did have one come in. Sharandeep, what lights are you using? Can you recommend some for measurement over 100,000 frames per second? That is a very specific question. Sharandeep, we might follow up with you after this. As far as that goes, today we were using GS Vitek lights, very high intensity lights, about 12,000 lumens as far as it all goes. But we would like to hear more about that application before suggesting anything one way or another. Kyle, did you have something?
Yeah, so just for Charandeep, just for that kind of application where you're working on really small scales, you're looking at really high frame rates, you're probably doing some kind of micro experiment. Typically what we recommend for those is some sort of fiber light. Photonic makes a great fiber light for this. It's actually an LED-based fiber light, so it's really good for illuminating really small fields of view and you get really high frame rates. So, and again, the lights are so bright you can front light or backlight, and we'll get with you offline and talk a little bit more about what you need. But yeah, I'd recommend probably a fiber light for that one.
Okay, and then we'll answer this one last question. There seems to be a couple more here, but we'll go through these last 2, and then we'll probably finish from there and answer any more questions offline. We have a question from David Molina. Do you have any tips to paint the patterns faster? So generally, most of the patterns that we apply are spray paint. It's a very quick process to do. But in circumstances where we're dealing with unusual structures, or if we have users that aren't very comfortable with patterning, then we also offer a patterning kit that has a whole host of different tools that you can use in order to pattern in a little bit more of a regimented way. So that's a possibility as well. Okay. All right. We have one more that we probably won't get to today. It's a little bit of a specific question. But other than that, I think we've wrapped it all up. Thank you, everybody, again, for joining us for this webinar. Hope you were able to learn something useful to you. Kyle and I have our information that will be sent out so that you can follow up with us with specific questions. Looking forward to supporting you all in the future. And thanks so much for tuning in today.